Hello and welcome to this low-level JavaScript series where we're aiming to build the world's first RISC-V processor on an FPGA using the TypeScript programming language. In the last episode, we were working still on the emulator at this point, and we implemented store instructions. And along the way, we actually made some changes to the system interface, the kind of memory mapped I/O interface that we've defined so far, in order to accommodate for the fact that we can actually address 8-bit wide, 16-bit wide, and 32-bit wide values. And we made some adjustments, and now we can actually go and implement load instructions as well. So that's what we're going to do today, actually, and I'm going to try, I say this every episode, I'm going to try to keep this one relatively short. The scope is pretty narrow, so we are indeed just looking at 6 instructions, if all goes well, and actually one of the 2 opcodes, if you will. So we have 5 load instructions, which is different to the 3 store instructions we had. We had store byte, store half word, and store word, but here we have load byte, load half word, load word, but we also have load by upper and load half word upper. So we have a couple of extra instructions there as well. And there is also this additional LUI instruction, which is load upper immediate, and that is its own instruction format. That is basically an instruction that is there to allow us to load immediate values into a register, actually. So not even into memory, but into a register. So it's not a load in the sense of the rest of those instructions, but I kind of put it in here because I thought it might be a useful thing to do here anyway. So that's the plan. Let's take a look. Let's first go to the spec and take a look at some of those instructions we were looking at. Here I actually have the page open for load upper immediate, but before we go to that, let's just look at the regular load instructions. Just those 5 that I mentioned before. So they're encoded here in this I-type format, I believe, which we've already dealt with because some of the ALU instructions come in this format. And what we're looking at here is we've got a 12-bit immediate, that's our offset, just like we had in the store instruction, but not distributed across these different, not distributed across the instruction encoding, as it were. It's just on the end, so it's easy to get at. And actually, we've already decoded all these values. We've got RS1, that's our source register, that acts as a base, and we take our base, we add it to our sign extended 12-bit offset, and we use that as the address to look in memory and grab a value. And funct3 here tells us like what the width is going to be, and it's not only going to indicate the width, but it's also going to indicate that other part that gives us those extra 2 instructions. Okay, let's see. Do they mention here anything about the those additional things? I'm actually going to do a little search here because what we have LBU, like load by upper. Okay, so what we have, LB and LBU defined analogously for 8-bit values. So here's what I actually want to check here, right? Because we're loading a byte, and basically what we're doing here is, okay, we can use the address to zoom in on a particular byte and load that. And my guess, right, is that the upper part, the U, is pointing that it should be going to the upper, and I expected that to be, I don't know, expressed somewhere. So let's see, LBU, covering up that with something. So let's go next. Okay, this is actually just the same text, but you can see this is referring to the 64-bit instructions. Let's see, do we mention it anywhere else? Here it is not telling us anything useful because it's basically the same as those other loads. Yeah. So what I'm wondering is basically we're loading these into registers now, right? We've stored a value from a register into memory, and now we're taking something from memory and we're putting it into a register. So my assumption is, right, and I don't really want to work on assumptions. I kind of wanted to read this out. Like this one is clear because LH and LHU. Oh wait, here we go. I think I actually just should have read the text, and I it's right in front of me. Okay, so LH loads a 16-bit value from memory, then sign extends it to 32 bits before storing in RD, and LHU loads a 16-bit from memory, but then 0 extends it. Okay, so I was completely wrong there. I had assumed that this was wrongly assumed that this was to do with where we were going to put this in the register, like where we're going to put it in the upper quadrant, where we're going to put it in the lower quadrant, whatever. But actually it's about signed and unsigned. So that's actually, obviously that's handy, because it means that we can actually load an 8-bit value rather than loading like, you know, like bringing a bunch of sign bits that don't really need to be there. Okay, so that's actually pretty interesting. I'm going to have to write some logic for that. Cool. I actually think we know enough now to go back to the code, and let's open up... where should we go to? We're going to need to go into decode. And one of the things we're going to want to know is, are we dealing with a load? So let's make a register for that. Is load, and, well, the spec tells us on page 104 that for a load, we're looking at this opcode. Is that the same between all of them? It is. That will make life nice and easy. Where am I? So here. Oh god, copying stuff out of PDFs, it's like nightmare material. Alright, that looks good to me, I think. You see one bit there changes between this load and store. Okay, and actually this is interesting because now we have this idea of like, if this was an ALU operation, then we would be loading the immediate 32 as the ALU immediate. Which is not true, and I think we should rename these because, okay, so darting back over to the spec again, basically where we're getting these immediates from is based not on like the specific opcode, but it's actually based on this instruction type. So like what we're calling the ALU immediate is actually just the I type immediate, and what we're calling the store, well in this case it is the S type, which I think is only used for stores. So yeah, that's kind of accurate, but let's actually name them after the instruction types instead, because then we can actually be super easily consistent about it. So I'm gonna rename store immediate to S immediate, and I'm gonna rename ALU immediate to I immediate. And then, hey, now it could be that we're looking at an ALU operation, or we're looking at a load operation. Is load next value. So now we actually have the right immediate loaded into our sign extended immediate value. And yeah, so we've decoded, we need to latch the value. Put this here. And let's also export it. Is a load. Is load. So execute, this is doing ALU related stuff, so at this point we don't need to do anything. This is going to be in the memory access stage. yeah, so here we're looking like, hey, is this a store? And here we're doing this thing that we're saying we should do in the ALU. Maybe we'll move that in this episode, maybe not. Hey, like else if this is a load, and we're going to get is load from here. And that's one thing we're not doing. We need to pass this through. So we didn't do anything in execute, but one thing we should have done is just pass this through. Great. Let's load. Okay, so now we have an is load. That should be a valid thing. And if we have a load, then we're going to do something. And yeah, we're going to do pretty similar kind of stuff here. So let's borrow this. And we calculate the address. Yeah, see, this is of course one good reason to just do this and think, because we're going to need the same address. Why don't we just, for now, we still need to move it, but for now I'm just going to move it out of here. Put it up there. Reduced indentation level a tad. Yeah, let's copy that switch. We're going to have a few more cases in here. One thing I didn't mention yet is that like you can imagine that someone feeds us a piece of code into the CPU. I mean, this wouldn't happen with a good, well-formed program, but you can imagine that someone might feed us a bad program, and we have space to encode 8 values here, and yet we only have 3 valid values. And so there are 5 possibilities here where we might actually just have something that makes no sense. And when that happens, we actually need to basically create a kind of exception in the CPU. And I'm not going to go into all the exception stuff now, because that is kind of an entirely different subject, but I do think it's worth mentioning just at the moment that like we're going to need to go back into like all these places where like decoding could result in something being an invalid instruction, just something we can't deal with. And in those moments, we're going to need to figure out a way to cause an exception to happen. And it will probably be worth figuring that out in the emulator ahead of time, because we can test it out with different things. I've actually installed all of the RISC-V toolchain stuff now, so at some moment when it starts making sense, when we've got enough, well, probably all, or enough of the instructions kind of set up, we can actually start throwing some real programs at this. We can write something in C, just actually have a program that's doing some stuff, and then put it into the emulator and just see how it responds, and then maybe we can start malforming bits and we can try to figure out how things should work in that way. But yeah, that's a tangent. Of course, there have to be some tangents here. So, alright, so now, of course, we actually end up with a few more possibilities here. So I might actually go in and, like, this kind of... Yeah, you can see that this actually gets a little bit weird now, because, like, in this encoding, let's just zip over to the spec, like, these 3 instructions, they're completely analogous, I keep saying analogous to the store instructions. So those first 3 values are the same, but obviously the minute we get here, actually this one, and you can see in the encoding, we really only care about those first 2 bits. Yeah, that's kind of it. Yeah, so, I mean, RISC-V has worked all this stuff out, for, of course, right? But only these first 2 bits actually encode, like, the width. And then this extra bit is just telling us about this this signed or unsigned thing. So this is the sign of... basically, this is telling us what we need to do after. So this is telling us sign extend, and a 1 is telling us to 0 extend. So yeah, maybe actually this doesn't matter, because we're gonna load something from. All it means is we need to only look at the first 2 bits here. So let's do that. Let's just ignore the first bit. Only look at the last 2 bits. So that's why we've put a 0 here. That will give us this part. And then what I'll do is, before we go into the switch, I'm gonna just create a boolean here, which will be like, are we doing sign extension or are we doing 0 extension? So let's say should sign extend, and that means we're going to just look at that third bit. So we're just going to say funct3 and ob100. Like if this if that bit is if that's a 1, actually if this whole thing comes to 0, then we should sign extend, right? And if it comes to 1 or anything else, of course, but just 1 in this case because we're only looking at 1 bit, then we're gonna 0 extend. That'll do it for now. I mean, this really could be a piece of decode logic, but it's sort of like also fine that it's not, because it's just looking at 1 bit. And in the FPGA, like looking at 1 bit of something and like us deciding what to do with this bit is like there's a way that we can make this non-expensive in the CPU, if that makes sense. Like for whatever expensive means in this moment, which I'm not going to go into. I spoke about it briefly in the previous episode. Okay, so what we're going to do is we're going to get a value. Just assuming everything is fine for now. So we're going to get a value, which is going to be a number. And we're going to assign that value to a bus read. And we're going to read from that address. We're going to ignore all that kind of stuff. And that's going to give us a byte. Value. Oh no, my shortcuts. I have no idea how that looked on video, if the window really changed there, but okay, so now we've read a value. We're going to break out of this statement. So then we're going to be at the end of the switch, having read our appropriate value, and then we're going to figure out whether we should sign extend it. So let's just do it like this: if should sign extend. If we need to 0 extend it, we actually don't need to do anything, right? Because 0 extending just means put zeros in the top bits, the most significant bits, and like that's going to be the case anyway, because we've read a value out, and like, you know, JavaScript doesn't really have this. JavaScript doesn't care; it's going to do that automatically. So if we should sign extend it, we're just going to take value, and we're going to do our sign extend trick. Actually, we kind of need to do the sign extension in the moment. Otherwise, we're going to have a second set of like looking at the width, because it's based on width. Remember, we've got this sign extend function. So I'll just do it like this: if should sign extend. Then we'll just say value equals sign extend 32. Right now we have 8 bits, so we have 8 bits, and our value is value. That's it. That's what we need to do, and we'll do that here. But this time we have 16 bits, and we don't need to sign extend a 32-bit value because we already have a 32-bit value. Okay, and so now we have this value, and we don't, in the memory access stage, we're not writing to registers. We do that in the write back stage. So all we're going to do at this point is we're going to pass along some information. So right now, because we didn't need them, we didn't actually pass on anything like the description of, is this a store instruction, is this a load instruction, whatever. We're not passing that stuff on at the moment. But we're going to need to do it, because when we go into the write back stage, which we have here, like here we're already like, if we have an ALU operation, that's the one we're passing on, right? So we don't pass on if it's a store or a load or whatever. If we have an ALU operation, we're writing our ALU result. Yeah, I'm just wondering, like from a design perspective, probably what we want to do is we only ever want to pass like one result through. So we don't really want to have an ALU result. We kind of want to have a write back value. And so it's fine for the ALU to produce an ALU result. We kind of want to turn that into a write back value. And then in memory access stage, we're actually going to work out, I think in memory access stage, we'll work out whether we're going to give back the ALU result or we're going to give back the load operation. Yeah, I think that sounds good. So what we'll do is we're going to rename ALU result to write back value. Just make write back one word there. I don't know if it should be like write back or who knows. Yeah, and you can see that we actually take ALU result in, but we say that write back value is the ALU result. And then what we're going to do is, if this is a load, which it is, then let's actually overwrite it here. So we'll overwrite this dot write back value dot value to be the value. That's fine, I think. Excuse me. Write back value. Maybe I should. So let's do it like this. Rename symbol write back value. Save. Because that will already change this one. Actually calls it write back value. That is the only problem with destructuring in TypeScript. When you come to use like the structural rename and that kind of stuff, it works really well. It will change all your imports. It will change, when you're doing destructuring, but it will like keep your name that you had before for something. And one thing I wish I could tell it to do, and maybe there is a way. If there is a way, then leave me a comment and let me know. But I wish there was like a rename symbol and but really rename all the things. Like actually, if something is like destructured and like give it the name that I'm giving it now, like that would be really nice. Maybe maybe there's a reason that I'm not thinking about now that could be the case where that's not really straightforward. Like I guess it could fail in the case that you already had a variable that had that name, but yeah, maybe VS Code could just give me an error message or something, like to say, hey, that failed because this thing is called that already or something. I don't know. It would just be nice. Like I've had this happen enough times now that I'm like, that's annoying. Pretty minor, but slightly annoying. Okay. So we need to pass if this is load on. So we're passing the ALU. Let's say it's load. We're bringing is load out already, so let's just do is load. Let's latch it. And let's pass it on to the next. So now we're going to have, if something is a load. And now the nice thing is we can do this, right? We can say if this is a load. Because it doesn't matter at the write back stage. We don't care where this result came from. We just have a result. We're going to write it to a register. It's that easy for us. Yeah, excellent. Cool. Okay. So if I'm not mistaken, that actually is already it. So I guess let's try it out. Feels too easy. Like it feels like something's gonna bite us. Like what? How many? It's so hard to get like out the window I'm trying to look at. We've only been going for 25 minutes. That's like record time. So, like, I must have done something wrong. Alright, so before we had this whole setup, went through a bunch of tests. Yeah, so let's do the same kind of test as before. We're going to write to... Yeah, let's have this be really straightforward. Let's have the base address be 0 or 20, the very start of RAM. Let's have... We don't have values to write anymore. We're actually going to have values that we want to check instead. Wait, we need... No, we don't. We don't have anything that we need to do here. Our source register is the same in all cases. Our offset is going to be defined by our immediate value. And the results, we're going to check them. So let's rename all of these stores to loads. And of course, this is a different format, right? So the format we actually have is that we have a 12-bit immediate. I'm just going to do this like manually now. Why not? Let's get rid of those. So what we've got is 12 bits immediate. Then let's double check here and not make any mistakes. 12 bits immediate, RS1. funct3 rd and then the opcode. Let's grab the opcode and put the opcode in. It's just the change in this bit actually, we know that. So funct3, that is moving to here. Immediate, source, funct3. I need to check again. I can't believe I need to check again. Yeah, okay. They are actually separated by funct3. Got in my head that somehow it wasn't. Okay, so let's do a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And let's put this offset by 4. This is going to be our base register. This is the source. So we actually want that to be... Is that true? Load store on page 31. RS2 is our source. Okay, yeah, so this is obviously, this is different between the things, and that's why I was getting confused there. So this is going to be our source, so we want RS1 to be our base. And this was, so it was 0, 1, and then 2, so this is indeed the 32-bit. And then let's store into register 2. Obviously it's a binary number, so we can't do that. Okay, cool. So we're going to load whatever is in memory there. So let's put a value in memory there, of course, ahead of time. So let's do rv.bus.write. We're going to write to address 20000004. And we are going to write the value beef. And we need to say that the width. And let's actually bring in the thing. What was it called? Memory width, access width. Word. Cool. So we should be able to tell after here, when we still have the debugger instruction, if we run this, we should see that value. Did it crash? What's going on here? Variable value is used before it's assigned. That's interesting. It says 92. So memory access 92. That is actually, yeah, okay. So that is a TypeScript thing, and it's saying to us basically in this case, right? Like there are cases where you don't assign value. So at this point, there's no guarantee the value is assigned. Yeah, the simpler, because I don't actually want to put a default case in here now because that's going towards the exception stuff. I'm just gonna do this for now, right? And we know that shouldn't be the case, so I'm sure this will come back to bite me. I'm sure of it. Okay, let's just try it anyway. So we got here. I guess let's do. Does that have enough? 1, 2, 3, 4, 5, 6, 7. Yep, done it again. So we got here, and we want to have a look at register 2. So let's say rv dot reg file 2. RV is not defined. Yeah, that's true. Make this mistake often as well. We need to be in the register file. That is a value, and tell me what the value is. The value is 0. Okay, let's set some more breakpoints. Let's actually see where we get into. Let's put 1 in memory access. Why not? And let's put 1 in write back. And let's run the program. So we seem to be stopping in write back. That's interesting. So what's going on here? Let's put a breakpoint at this point instead. And I guess let's have a look into code because maybe I just did something wrong here. Looking right. Let's have a quick look at the thing that I actually put in here. Is it really the thing that I think it is? Let's actually copy it. I did copy it before and I just didn't paste it. I made this change instead. Looks fine. Okay, let's trace it through. Let's see what's going on. So is load is 0. Is store is 0. Okay, we go even further back. Let's put it here and see what the opcode is. Opcode next value is 3. Well, that is 3. So this expression should come out to be true, right? That is true. Are we not passing this value on? Is load, is load, is load, is load, is load. We're latching it. Is load latch next? Okay, then let's see what's going on because is load, the next value is a 1 and the current value is 0. That's fine. Here we look at next value. Here we look at next value. So at this point we are assigning this one as our immediate. So that's all looking good. Let's just drop a breakpoint here. Get to that point. Take these out because that seems to be working fine. So we've latched. So this dot is load dot value. Now it's a 1. Great. And so that should also be a 1 at this point. So we went decode, then we're going into execute. Yep. I mean, there's your problem. Excellent. Cool. That's fine. That means we can already take out a few more of these breakpoints wherever they may be. Let's optimistically run it and see So, okay. Yeah, okay, because I took that out. Fine. Let's leave the suspense in. Boom. That is dead beef. Nice. Great. So let's try another. Let's try a 16. Simple to change. And let's do the same thing we were doing last time, which was to just move the offset a bit. So let's put our offset at 6 instead, which means we'll write into the second half of the 32-bit word at to blah 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 4. Hope that makes sense. And let's write register 3. Wait, no, this doesn't make sense. Actually, you need to look at a different address. I mean, we could do this because this would just, all that's going to happen here is we're just going to load only a part of that. So I guess that's actually useful to look at. So I'll do that. Let's just load, I guess, the second half of that into register 3. And then let's just put at 0 OXFF, why not? So we'll write a byte there, and when we do a load 8, we'll have a 0 offset, and we will write that into address 4, register 4. Alright, so first one, I mean, nothing should have changed, so let's just skip to the next instruction. So there's that one, and if we look at 3, we should see a different value. That's interesting, because that looks higher. Did I initialize RAM to just be FF? I think I may have done that. I don't remember, but I think I might have just initialized RAM all as FF. Or do the registers just get FF if they don't have anything in them? It's kind of weird, right? Oh no, it's sign extended. It's sign extended. Yeah, no, this actually makes perfect sense, of course, right? Because like this, the last number here is bigger than 8, which means it's gonna have something in the sign bit down here. This, if I just show you, I mean, maybe this is completely clear and it's not necessary at all, but if we just look at beef as a binary number with 16 bits, you see that we have a 1 up here in the 16th position. So yeah, it's sign extended, so that's why we're seeing F. So that actually makes perfect sense. And it's a nice test for us to be able to do the unsigned thing. So let's do that. Yeah, I shouldn't have actually stopped. Let's oh, this is great actually, because when we do the load 8, that's going to be so now I've actually skipped ahead. So that was that one, and then this should just be all Fs. That's interesting. That's really interesting. That doesn't make much sense to me. Let's see what's going on there. I guess maybe I messed something up. Maybe sign extension is working weirdly here. So let's just see what happens when we read this value. So I was expecting that. Hey, right back. Oh yeah. 1, 2. Is it me? Yeah. Okay. It helps if you actually execute the instruction that you think you're supposed to be executing. 1, 2. Actually get here now. Let's just optimistically go past. Take a look in register 4. All Fs. Brilliant. Alright, so now we've got our additionals, which is going to be the U. Let's line everything up nicely. And so with a U, what we actually have to do... What am I doing? Struggling to find the thing here. We need to put our 1 in there that tells us this should be... I'll put them in the same registers, and then what we should see is that when we run these 2 instructions, we don't get the Fs at the beginning. Did I do a refresh there? I did. Alright, so running the 32-bit, running the 16-bit, running the 8-bit. So they should all be in now. So was that register 2? We have dead beef. Register 3 we have FF beef. Register 4 we have all Fs. We go again and again. Now check in register 3 we actually just have beef. Register 4 we just have FF. Brilliant. That is everything that should be. Presumably all that sign extension stuff should work, but maybe it's worth testing. So yeah, I'm just going to test it with the 32-bit because that should tell us everything we need to know. So 32-bit, let's put all 1s here, and let's write dead beef into that, and let's say that when we execute that we would expect dead beef to be in register 1. So let's do a refresh and just look in register 1, register 2 rather, and it is there, so that's good. Sign extension works. Brilliant. Okay, so as far as the 2 points on the agenda go, those 5 instructions are now done. I'm sure we'll find problems with things down the line. Like, I'm sure I'm writing bugs that I'm not finding in my like very minimal testing. And something I might actually do is like off camera, like write some actual tests, write some unit tests just to like sanity check this stuff in between, and just codify some of the stuff that we're doing here now in like maybe a more concrete programmatic way. But I think that's relatively boring to do. It's like nice to attack the problem and then like testing and making sure everything is like working well. Although it is a very important part of doing all this stuff, I think it's less interesting for the videos themselves. So let's have a quick chat about LUI. Yeah, because this is actually where I got confused. Because LUI is load upper immediate, and it's this very first instruction here, and you can see that it uses a different format. It uses the U-type the U-type instruction format. I wanted to say that, where we actually have 20 bits, and just a destination. And the idea here is that like we're not loading from memory into a register. We're loading an immediate value into a register. And we're like devoting as many bits as possible to the we're devoting as many bits as we possibly can to like making an immediate of that size. So that's the idea there. And let's take a look. Let's actually find the first instance of that. So that's here, and it's related to this AUI PC, which is add upper immediate to program counter, which is here. We're not really gonna like. The thing is, these are 2 related instructions in the fact that they share this instruction format, and they're kind of doing the same thing. except one is specialized in the program counter register, which is not a general purpose register. But it kind of like this instruction allows the program counter to be a read-only, like not a read-only, but it allows it to be like read in this very specific way. So what we could do is like if we just wanted to read what was in the program counter, we could do add upper immediate to program counter, just add 0 to it, and then put it in some destination register, and then we would actually have the value of the program counter. But because most of the time if you do that, what you're going to want to do is like make a new address of some kind, and often, well, especially in this case, we want to make some kind of relative address. So you would have this upper immediate, and you would add that to like the program counter. That's it, pretty much. We're not dealing with that now. So yeah, there's actually a note about how add upper immediate when like used in combination with this other jump instruction can basically allow you to control program flow to like any different place. And that is like, if you remember in the introduction video, we talked about how RISC-V, it packs everything into 32 bits, which means we can't, instructions are packed in 32 bits, which means we can't specify 32-bit values, which means we don't have access to the full address space when we're jumping around and doing things. And obviously, like, sometimes you need that, right? This is just a mechanism to like allow you to move all over the place in memory. All right, forget that. It's a complete tangent. Don't forget it, but it's not what we're doing now. Load upper immediate is used to build 32-bit constants and uses the U-type format. Load upper immediate places the U immediate value, which is this, in the top 20 bits of the destination register, filling the lower bits with zeros. So basically, we're not zero extending in this case. We are, I don't even know what you would call that. Zero filling? Is that a term? I don't know. So that's it pretty much. And you might wonder, like, why do it this way? Why not put in the lower bits or something like that? And the reason is that you can really easily add to this register afterwards. And like if you start adding to this, like you can already like get the full 32 bits. So if you could have load upper immediate followed by an add to that register, writing back into that register, so referencing itself and writing back into it. In 2 instructions, you can form a 32-bit value. So that's it. And if you use an add immediate, then you can specify immediate values that way. Easy. Cool. So should we have a crack at this? Why not? Cool. So let's go to 104. And so the other one was 14. Let's remember that if we need to jump back. Load upper immediate. We've got this as our opcode. So it's actually it's a very different opcode. It's almost the same opcode as this one. None of that stuff really matters. All right, so let's go back to the code. Let's go to decode. Let's give ourselves a new one of these. I'm thinking to pack these up into a little like useful package, because these are going to move through the like, at least for now, we're like moving all of these values through the pipeline stages. And it might just be nice to like not have to unpack each one, pack it back up and send it along. It might be nice to just like, I don't know, maybe it doesn't matter for now. It certainly doesn't matter for now. So I'm just going to call this one is LUI, because this is the only instruction. So is LUI. Let me grab the opcode. Should have done that already. Copy. Back here. I may not have copied that. don't get this because I'm just highlighting that portion and somehow still getting this janky all over the place thing. Just going to line those up just because I think it makes it a little bit easier to look at this kind of thing. It also might be nice to not do this tricky like this tricky masking thing and looking at that and actually just compare the two values. Like the masking thing might be something to do in the actual FPGA, just to, you know, save a bit of like resources, save some resources. We don't really need to do it in the code here. Maybe it's clearer, but doesn't matter. Okay, so we know if something is an upper immediate. So now let's actually think about getting the upper immediate. So this is going to be the U immediate, and we don't actually need to sign extend anything here. What we actually need to do, if we go back to page 14, is we just want to get bits 31 down to 12. And what we actually want to do is then mask off these bottom 12 bits. Like, we don't care about those bottom 12 bits, we only care about the top 20 bits. Just thinking about what is the easiest way to do this, because we could also do this, like, we could make a... Like, we could shift these bits down and then shift them up. Like, we could write a method for 0 extending. Like, not a method, but a function for 0 extending, just like we have for the sign extend. That would probably be the most descriptive thing. So then what we would do here is we would shift down by 12 bits, and then we would shift back up by 12 bits. That's pretty much it. Let's do that. I think that's going to be the clearest thing for now. So let's take a detour, go into the utils. Or util rather. So we'll make this 0 extend to 32. No, that's not even what we're doing here. That's the point, that we're not 0 extending. We're actually filling the bottom with zeros. That was the whole thing. So what we're going to do is we are going to take the instruction. We are going to shift it down by 12 bits, and then we're going to shift it back to the right by 12 bits. So we're just like chopping off those bottom 12 bits basically, and that should work for our purposes. And now we can add our new else in here. So our new else if this dot is a lui dot next value. Well, if that's the case, then our immediate is going to become U immediate. Yep, that's that. Let's pass along the lui. Let's grab it from here. Is it meant to be pronounced Louis, like gooey, like GUI? Who knows? One of life's great mysteries. We're going to need to feed that through the execute stage, even though we're not going to do anything with it now. Great, and then we're going to get to memory access, and we don't need to do anything with it here because we don't. That's not the place where we're going to do it. We're only going to do this in write back, right? We're writing an immediate value. Although, it's interesting because we have this write back value now, and depending on whether something is a load, store, or whatever, we're now doing our thing. So if this is a load upper immediate, then this dot write back value is going to equal immediate 32. That's easy. That's so easy. And then if this is, so maybe we could even, I'm just thinking about if we can just know, no, let's do it like this. We made that, let's pass the value along. So is load upper immediate. Pass it on. And we'll just pull it out and do it like this. I'm fine with that for now. Great, let's try it out. Let's see if that works. Don't need any of the setup. We'll leave one instruction in place. And let's go and grab let's go and look at the format. So yeah, we have 20 bits of immediate. We have the destination register and the opcode. And the opcode, I mean, might be good to just give these like constant names somewhere. But for now, I'll do it manually, deal with the jank. So let's write into register 1 just for the ease of it. And then all these other bits are going to become our immediate. So what immediate value can we write here? Well, we could write something super easy to see, like 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 16, 18, 20. Yep, that would be super easy to see. So that's going to be like a bunch of 1 zeros followed by 12 zeros. Let's take a look, and this is going to be load upper immediate. Will it work? That is the question. That looks good. That actually looks like perfect, actually. Yeah, so, you know, the whole 0, 1, 0, 1, 0, 1, 0, 1, that is A, or AA in hexadecimal. And the fact that we have AA, AA, A means that we did that we have 12 bits left over, and we wrote, what is that? 20 bits, obviously. So that works. That's awesome. And I guess just to prove, because we actually have the adds, right? So let's just let's make an add upper immediate here, and then we add so we're adding a 12-bit immediate. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We're going to have a source register, so that's going to be 1, and then we need to have the correct thing. Which, wait, are we exposing that in the execute stage? Do we expose this thing? We do. So yeah, we can actually do that directly here. No, that's too much work for now. I'm just going to grab it. It happens to be 0. That makes things easier. 0, 0, 0, and then destination 5 and opcode. Yeah, should have looked at that. I'll grab it from the spec. Why not? So this is just to check the like, hey, can we actually load 32-bit immediates? And obviously we know that we can, but something doesn't look quite right here. So we have 1, 2, 3, 4 things. Okay, that actually looks fine. And here we have 2 of them. Maybe it's just my eye looking at that wrong. Okay, apparently it's fine. So what we should see is that now that this whole thing should be A when we execute. So we run again, and then all. Oh, that's not right. But that might be my fault. Oh, that's interesting. Okay. Did I mess something up here? Did I actually maybe didn't? Yeah. Okay. I think I've just messed this up because add I did and I. That should work. Right? They are the same opcode. Source, destination, they're the same anyway. 12 bits. That is actually really curious. That is curious. Because I would have expected that to work fine. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, I would have thought that that would work. Mystery. I'm actually gonna put a breakpoint down in the execute stage. Alright, so it's not a register op. So we come down here, our immediate 32, well, that's not telling us much. Oh, it's sign extended. Yeah, well, I guess that makes sense. That's actually really interesting then. Yeah, like how would you... I guess I'm going to look into that another time, but this actually is fine for now. Like, I've just misunderstood how this thing works, because obviously, yeah, at this point that is going to be sign extended. I guess you would have to just like and it off. I don't know. It seems weird. Anyway, it works at least the way it's kind of described. Anyway, so I think we made pretty good time in this. It seems to work. I'm pretty happy with that. We've got loads, we've got stores. That's really important stuff. And if we just take a little peek back here, we now cover like this instruction. We cover all of these. Actually, we cover all of these now. That's a huge chunk of the instruction set. And you can see that what we have left are this add upper immediate to program counter, which we've discussed, which is actually really easy. I just need to think about how I'm going to do it and where I'm going to put this, because I actually don't want to have, like, in the hardware, I don't want to have loads and loads of add circuits, because, you know, that's not really the idea. I mean, I think having a couple of add circuits is going to be okay, but we're going to have more than this, right? Because every time it's kind of not the point right now, but also in instruction fetch we have an add circuit, right? Because we need to add 4 to the program counter every time. So there is also an add circuit there, and it's unavoidable. But yeah, we need to think a little bit hard about how to do that. I'm probably not going to think too hard about that now, or in the coming episodes. I'm probably going to do that in the stupidest possible way. You know what? I might even just do it in the stupidest possible way anyway. For now, and then we'll tackle that later. We've got these 2 jumping instructions. And so we're going to look at that. We're going to look at dealing with that crazy immediate decoding. I don't really understand why it's this way, but we'll get to that. Then we have the branch instructions. They should be pretty relatively straightforward. Branching is, of course, actually quite a tricky subject. Again, it won't be in the processor that we make right in the beginning, but branching is quite a big subject in processor design, because like it's the biggest source probably of like what holds processors back from being fast, because you've probably heard of things like branch prediction. Yeah, and we're not really going to have any branch prediction in the beginning because we're going to have a non-parallel pipeline. So why would you have branch prediction? It doesn't even make sense at that point. But when the pipeline does become parallel, there is going to be at least implicit branch prediction, because we're just going to, and RISC-V actually mentions something about this. It mentions that you should just assume that branches are taken. So like, is it assume that branches are taken or assume they're not? In either case, if there's a branch, you start like just like running the pipeline as if you're going from one point or the other. And you can actually go and build crazy circuits, and they're described in books and stuff, and I'm not going to pretend that I know tons about branch prediction because I don't. But there are circuits that you can build that can actually get really, really good results. And like, you know, the processors that we use today, they predict branches really, really well. The branch prediction stuff also allows for, you know, really untold, horrific computer bugs that we've seen in the past few years. But that's not really anyone's fault. That's just that's a side effect, literally. Anyway, we've got these branch instructions. They shouldn't be too hard to implement. Then we have fence, something that we're not going to worry about because we don't have we're not going to have multiple cores. We got to think about these two instructions, eBreak and eCall, which are kind of debugging kind of things, I think, and they might also pertain to exceptions. And then we have these CSR based things, which are system, said that really enthusiastically, system instructions, which I won't get into now, but basically like they allow you to, this is how you go in and change like kind of settings. You get information in and out of the processor. This is how you change its state internally. And that's they're used for everything in like the RISC-V, especially as you move into the privileged architectures, or the privileged specifications. They become really important because like they allow you to, you know, kind of communicate between different privilege levels to kind of set things up in the right way. They're slightly less important for us, and there's only a few things that we really need to do. I might even skip those in the beginning. We'll see. But yeah, so, and this is, there will also like, no, it's not for now. It's not a topic for now, but like you can see that we're actually kind of getting to the point where we're almost there. And certainly we're getting to the point like when we have jumps and branches, we'll be at the point where we can actually compile programs and run them. Like, yeah. And that'll be a really exciting step. And I think before we've finished like those parts, you know, these parts here, before we've gotten to those, we'll probably be actually compiling some C code and running it on the processor just to see if it's all working the way I think it should be. Anyway, thank you for joining me today. I'm really glad you're on this adventure with me, and I'm having tons and tons of fun doing this at the moment. I really enjoy thinking about and just like attacking this processor. I just wish I could be doing more and like running through it even faster, but you know, things take time. So thanks again for joining me, and I will see you next time.